So thank you for the nice introduction, and thank Dusa and Christine. There's Christine for the invitation to be here, and thank all of you for coming on a nice day, being inside instead of outside. Okay, so this is going to be a very high-level view, 10,000 feet of different kinds of mathematics that one can do with networks, different kinds of networks. So I call the age that we're in the age of networks because everywhere we look, we see networks. I mean, there are technological networks, the internet, the World Wide Web. There are social networks, of which, we think most now of social networks on the World Wide Web. Gene regulatory networks, resource allocation networks, so many different kinds of networks. So what I'm going to do first is talk about what kinds of networks I want to try to say something about. Then some problems that we can formulate on these networks that will involve graph theory and combinatorics, of course. Networks are graphs, so there will be a lot of graph theory here. And then I'll spend a little longer on a couple of problems. So, okay, so as I mentioned, there are lots of different kinds of networks. So let me just tell you some of the networks that we would like to talk about. So technological networks. So we model these networks as graphs. They have vertices and they have edges. So the AS Internet, the Autonomous System Internet, so the different systems on it can wall themselves off from the rest of the internet. So AOL, MSN, Yahoo, IAS.edu can wall itself off if it wanted. Okay, and the edges are the connections. There are also digraphs, directed graphs. So the World Wide Web is a digraph. There are hyperlinks which point from one website to another website. And then there are lots of other kinds of networks. Cloud computing networks, networks of data centers. So here, there's a lot going on at the different nodes of this network, and there are capacities along the connections. And actually, some people in our lab and in many places now are thinking a lot about cloud computing networks because something like 3 to 5% of the power consumption in this country is being used by cloud computing networks. So when you do a search, you think it's free, right? But there are all of these machines that are computing something when you do a search. And we're putting more and more onto these cloud computing networks. And the 3 to 5% sounds scary, but what's actually a lot scarier is that it's doubling every 5 years. Okay, so that can't continue for too many more cycles, but we're going to run into problems if we don't think of good algorithms on these networks. So I met a woman at lunch who's doing algorithms on graphs. There you are, okay? And she's working with Mark Jerem. Well, think of how to do better power consumption on these graphs, and you would really help a lot of people. Okay, social networks. So there are offline social networks, which people have studied for years. The spread of disease. When we were worried about SARS spreading, we were looking at offline social networks. There are, of course, many online social networks that people look at. This is a representation of a Facebook graph. There are actually really interesting problems even in how you represent these graphs. How do you visualize them? And how do you cluster them? So there are all kinds of really interesting graph theoretic problems here. And it's nice because, I talk to young girls about going into science, and a lot of them are looking at things like this, and they have no idea that mathematics and engineering are such an important part of studying these networks and of setting them up in ways that are interesting from a social perspective. Okay, there are many other networks. There are mobile phone networks. There's been research on mobile phone networks. I actually find the research really scary because we have to be very careful as we do research on social networks that involve personally identifiable information, PII. The first large-scale study of a mobile phone network was funded by the National Science Foundation, and they actually did a study on the Orange phone network in Europe. And from the data that these guys published, it was either Science or Nature, you could actually go back on the online data and you could figure out who was calling whom in many cases. So there are all kinds of privacy questions that you have to layer on top of this. Cynthia Dwork is a cryptographer who now has spent the last 10 years coming up with notions of what it means to keep something private. You know, I mean, putting epsilons and deltas on this, okay, so that you can guarantee a certain, you can guarantee privacy with a certain probability, provided that you ask no more than so many questions of a data set that is so large. And so those are really, really interesting questions that you then combine with game theory and combinatorics. Instant messaging networks, microblogging networks, many of the same issues here, but the structure of the networks is different. Twitter is a directed graph, right? If I follow you on Twitter, that doesn't mean that you follow me on Twitter. Okay, economic networks. So these are really, really interesting. The AS Internet has 3 tiers. So if you're a member of the highest tier, like AOL would be a member of the highest tier, then you can ask one of the lower tiers to carry your traffic and you don't have to pay them. If you're a member of the 3rd tier, you have to pay the 2nd and 1st tier to carry your traffic. If you're a member of the 2nd tier, you have to pay the 1st tier to carry your traffic. And so when you start to look at the routings, and you can think of these routings as processes on these graphs, if you think of the routings that result, they are strongly influenced by cost, which makes them vulnerable in certain ways and inefficient in certain ways. So you then take something like graph theory and you combine it with game theory and other kinds of mathematics. And one of the really cool things about graph theory and combinatorics is you can combine it with these other disciplines of mathematics to model the real world in many interesting ways. And the problems are also mathematically fascinating. There are market networks, you know, buyers and sellers and intermediaries. And in general, just bipartite graphs of buyers and sellers. There are huge numbers of people who work on ad auctions, which is, you know, advertisers buying ads on Google or Bing, okay? And and you have to look at the bipartite graph of the advertisers and the people who are searching. So those are also very, very interesting graph theoretic problems. Okay, biological networks. Well, for many years, people have studied phyla. You know, what we see the species that exists now. How from that do we infer how we evolved? Okay, and these are very interesting questions. People like Tandy Warnow at Austin study this, and she has all kinds of theorems about what you can conclude and can't conclude from the data. These are large-scale questions. People also look at things like the AIDS virus and study, you know, try to trace where it came from by looking at similar kinds of questions. Okay, gene regulatory networks. So I'm going to talk more about this later, but you know, on a very crude level, what happens is that you have DNA going to RNA going to proteins. The proteins then sit on the DNA, and they cause parts of it to be transcribed more and less, and so you've got a feedback loop there, which is very interesting. There are real neural networks, many interesting questions. Okay, so what are some of the problems, the mathematical problems that we could pose on these networks? Okay, well, I'll talk about 5 classes of them. So modeling networks, how do we take the properties that we know and try to model them? Sampling, since these are very large networks, you may not be able to take in the whole network to do a calculation on it. So you need a good way of sampling where you can, prove to within some probability you've actually got a good sample and what you're saying makes sense. Processes on networks, so you have a network and then you have a virus spreading on it or something. That's a process on the network. Algorithms on networks, so if you have a network, can you construct an algorithm which does something that you would like it to do on that network, or a network reconstruction algorithm, so you see some output, which is some partial information. How from that do you infer the network most likely to have produced that information? So that is a kind of inverse problem, a combinatorial optimization problem. So that's your combinatorics in action. Okay, so modeling. So first of all, what properties might we want to model for some of the networks that I had mentioned? Okay, well, many of them have small diameter. So people often think of Stanley Milgram when they think of 6 degrees of separation. So he was a sociologist in the 50s who gave postcards to certain people, let's say in the Midwest, and said, okay, I want you to send this card to someone who is an elementary school teacher in Massachusetts, or let's say in the Northeast. Okay, and so who would you, and it had their name on it, but nothing else, no address. So this is really a local algorithm. If I think there must be some path from me to this unknown person, okay, I don't have global information on the network. All I know is the people I'm connected to. So how would I send it? To whom would I send it? On what I hope will be the shortest path from me to them. Okay, so you might say, oh, I'll send it to the most famous person I know, and then he can go to the most famous person he knows, and then they can go back down, maybe, or maybe not. Okay, so what the experiment showed was that people are typically six degrees of separation apart. Actually, this was already in a Hungarian story in 1929. I don't know how he managed to get the 6 degrees there. And there are, in fact, Facebook experiments in the last year which show, again, it's about 5 degrees of separation or something. So any 2 people on Facebook are, maximum of about 5 hops apart. Okay, power law degree. So you probably have been studying random graphs, have you? Exponential distribution, yes? So, just things are, there's probability P that any node is connected to any other node. You have n nodes. So those fall off exponentially. Those have an exponentially fast fall off. The kinds of things that we observe in social networks fall off much more slowly. So if I ask, what is the probability that I have k neighbors, instead of falling off like e to the minus some constant times k, as it would in the random graph, because I have to have, a connection that costs me p, k times, that's the leading order term. Here, it's going to fall off like 1 over k to a power, so much more slowly, much longer tails. And these social networks, these technological networks, a lot of people say the signature of human activity, because the technological networks are reflecting something about the people who've built them, are these long tails, these power law tails. Okay, and then aging of vertices. So on both the autonomous system internet and the World Wide Web, older vertices tend to be more highly connected. Not always, but often. Okay, and this is in fact the basis of an industry of web spammers. So what happens is that when an old name, when an old domain name goes out of use and it's not renewed, no one pays for it, it gets picked up by these search engine optimizers who then buy that up and they create links from that to your website to move you up in the search ranking. Let me go to the next page and tell you why they do that, how search engines work, okay? So the early search engines used language, used the words on the page to find the most relevant web pages. Okay, that didn't scale very well. The later search engines used the structure of the web graph, so graph theory and algorithms, to find the most relevant web pages. So this is a very simple algorithm that they use, the PageRank algorithm, which is named after Larry Page, who is head of Google. Okay, and he did this in grad school, actually. He and Bryn did this in grad school. You do a random walk on the web graph. So the web graph is a digraph. I'm going to take a random walk on the links of this graph. Now, if you think about it, you might just get stuck because you might go into a site which has no outlinks, okay? What if there's like, what if you put your paper on your web page and there are no outlinks in your paper, then you just get stuck. So restart every, say, 7 steps, or with probability 1/7 or something, restart. Okay, either you can do it either way. And you keep doing this again and again until you get to a stationary distribution. Now, it should be clear to you that the weight is going to be much higher for things that have a lot more inlinks, but not just a lot more inlinks. Also a lot of inlinks to the things that are linked to them, because if I had a ton of inlinks but hardly anything got to those, that wouldn't help me, right? And so what the PageRank is the stationary distribution of this process of doing a walk. And so to lowest order, what you see in the search results is you see this distribution. So you see, you put in the word roses, and what they do is they go through all the web pages and they pull up the ones, not the ads, they pull up the one they're going to display on top is the one with the largest ranking in that stationary distribution. So what would you do if you were trying to spoof this? So I don't want to pay for an ad. I just want my website to organically appear on the top. I would create a lot of links into it, hoping that that would raise me up, right? But I would have to create a lot of links into it from something which itself had a lot of links into it. So now let me go and buy some old domain names that had a lot of links into them. And let me do that. And that's what web spammers or search engine optimizers do. And in fact, Google started pulling these sites out. They said, oh, these are being web spammed. These shouldn't be up in the search results. And then some companies said, Google is ruining my business. They have no right to ruin my business. And there was a lawsuit over it. And we did something different, which is we said, let us just detect anomalies. Let us, as we're taking this random walk, if something seems to not feel like the rest of the place that we've been walking, we actually did some backwards random walks and stuff, but it doesn't really matter. If it feels anomalous, let's not throw it out, but let's just down weight it. Okay, so if it in some way is not appearing like the rest of the web, we downrate it. And that automatically pulls those things down. You don't have to do it manually. And so it would be much harder for somebody to go in and sue an algorithm than to sue a person or to sue a company. Yeah?
How does that process depend on the word roses that I put in?
So what they do is they find something that has the word roses in it and is the highest in the ranking. And then they do a ton of other things. I mean, it's the lowest order, it's that. But then they call these things features. So the biggest feature is the word you put in. But then there are other things, like if it happens to be the web page of a person or a business, which they recognize in certain ways, then that also gives it a higher. But this is the lowest order, what they're doing. So they're finding everything which has the word roses in it, and then they're ordering those. So if you go to page 347 and you go to the 2,892nd entry, it's the 2,892nd thing in the relative ranking of the web pages that have roses, have the word roses in it.
So I just do the random walk amongst the roses?
No, so it is, this is why it costs so much bloody money. Do you understand what they're doing? First of all, there's about 1 trillion web pages, okay? So you don't pull in 1 trillion web pages and do the stationary walk on 1 trillion web pages. So you have to sample properly, which I'm going to get to at some point, okay? So but if you could just do the whole thing, you would take that 1 trillion pages, you would run it until you're very near the stationary distribution, you would look at the relative ranking and the stationary distribution of everything which has the word roses in it, and you'd be done. Okay? I mean, that's the lowest. This was basically what Brin & Page took to, to venture capitalists. Okay? And then they made it better and better and better. Okay? So there's graph theory. I mean, it's all graph theory, really. Okay, so modeling networks. So I'm going to tell you quickly about 3 kinds of models. First, growth models. So these are probabilistic models. So what happens is, at each point, a vertex comes in, and it attaches to some other vertices that are there. And the probability, or let's say, it attaches to M old vertices. The probability that it attaches to any old vertex is proportional to the number of things that are connected to that vertex already. Okay, so this is a rich get richer phenomenon. You walk into a room and you go up and you try to talk to the person everybody else is talking to. Okay, I mean, some people don't do that. Some people do just the opposite. But if you were doing this model, you would say, I see 30 people in here, and wow, that person has 6 people talking to them. Okay, with probability 1/5, I'm going to go talk to that person who has 6 people talking to them, and so on. Okay, so the first rigorous work on this was in 2000. Oh, and what they showed is that this has a lot of the properties that they want. Okay, this has power law tails, this has a small diameter, has a lot of these nice properties. Okay, then there was a directed preferential attachment model that we did a few years later, which is a directed graph. It kind of algebraically got to be worse, although if you're like Margaret, you probably think it got to be better because you'd have like all these beautiful special functions popping up all over the place, okay? And then you feel really good, and you're like going back and looking at Whittaker and Watson and just feeling like you're connecting somehow, okay? Okay, so preferential attachment with fitness is another model. So here, there are different, so some people link to Facebook, some people link to MySpace, okay? MySpace was earlier than Facebook, but Facebook has more people who link to it, okay? It's because it somehow is fitter. It was born with greater fitness. And so here the model is that when you're born with a particular fitness, and the probability that a later site will attach to you scales both with the number of connections you have and with this fitness that you were born with. And the fitness is chosen from a distribution of fitnesses. And it turns out that there are 2 phases. So here's a phase transition depending on the fitness distribution. So one is what I call a fit get richer phase. So the power law will depend on the fitness. But the other is, it's a really interesting phase. We gave it a name that sounded cool, innovation pays off. But basically what's going on is that there's a phenomenon in physics called the Bose-Einstein condensation, where particles that have a certain statistics all pile into the ground state, and you get really bizarre properties, and you see this in low temperature physics, really, really bizarre properties. And what's going on mathematically, which is really pretty, is that you have a certain integral that's diverging, which corresponds to all these things pouring into this ground state. And you see exactly the same integral diverging here. And what it's representing is that a positive fraction of the mass of all future things are going to attach to this one site. So it's going to be like a monopoly in which they get a positive fraction of everything forever. Okay, so you just change the fitness distribution various ways and you get this really interesting phase transition. And you can contrast this with a single phase of the standard model where, you know, first to market is everything. If you're the first one born, you just get more things attaching to you with high probability. Okay, so there are also competition models. So here you have an optimization problem in which when a new vertex comes in, there are two competing factors. And so every time a new vertex comes in, you do a little optimization problem to figure out what to attach to. And it turns out that you can get some really interesting graphs by doing this. And when we did this, we were able to explain the kinds of graphs one sees in the structure of the AS internet and some other things. So really some pretty results. And then there are fully game theoretic models. As I was alluding to earlier, game theory is a really nice thing to combine with graph theory. A lot of economics now is done using game theory, modeling people as strategic players in a certain game. And if you do this on a graph, what the graph is telling you is that I'm allowed to interact with any of my neighbors. So if I have an edge to someone, then I'm allowed to interact with them and I have a strategic game going on with them. And so what you do is you then act based on this to maximize a certain function, and you keep going around and going around until you reach an equilibrium state, in which things remain stationary. Okay, so there's some nice probability, and there's game theory, and there's graph theory, and this is the way to describe the economics of these networks that you see all over the place. So you have mathematical economists doing this and computer scientists doing this. So it's a really nice kind of thing to do with graph theory. And so we did some work on this with some of our interns and postdocs in the past. Okay, sampling. Okay, well, the World Wide Web is very large. It's on the order of 1 trillion static sites. So a static site as opposed to a dynamic site, every time you open up a web page, there are new ads put there, or you search and new things come up because that's a dynamic web page. That was caused by you opening it. But there are also static web pages out there that people have made that don't depend on someone opening them. There are over 1 trillion of those. So, for example, if we want to calculate PageRank, okay, I want to find the stationary distribution on this directed graph of 1 trillion sites. Well, geez, that's going to take me a long time, okay? So I want to know how to sample from these graphs and how to test these graphs and know that what I'm doing makes sense. Okay, so in about 2005, Christian and I started talking to Latsi Lovas and Vera Shoj and Kati Vestergambi about how one does that. And we just thought, well, there must be some well-known limit of graphs, and we could look at that. And then we could say something about the properties of those graphs and how you would test from the limiting graph. Well, it turns out that there wasn't a theory of graph limits and testing. So over the last 7 years or so, we've developed a theory of graph limits and testing. And there's really, really nice mathematics here. It turns out that you can represent the limits of graphs as certain kinds of functions. And then in the same way as working on a differential equation is often easier than working on an interacting particle system, in the limit, all of the approach to the limit gets wiped out. And so the properties are simpler. Now, you can't say as much as you can, yeah?
So you're saying the initial paper by Lujas and Segedi was inspired by this web?
Ours was actually done earlier than that. Yes. Okay. Yeah. So yeah, it was done about a year earlier. So we did the talking about what the limit was and how you approach the limit, and they got what the limit was, but we defined the process of taking the limit and the metric to take the limit. And we showed that there was a limit, we just didn't show what it was. And then Lujas and Segedi showed what it was. It was inspired by the web. Yeah, I mean, it was inspired by, actually, we were working on the web spam stuff, and we were saying, how does one possibly do this? And then we went to Lotzi and we said, you know, it must be, because we're physicists, and we know that physicists take thermodynamic limits of everything, so of course graph theorists must take limits of graphs. So what are limits of graphs, and how do you characterize their properties? And that's where it all started, yes. And Vera Shoge happened to be visiting, which is great because she's one of the great combinatorialists of all time. So anyway, yes, so this all came from there. It came from asking about these. So, you know, it is not just the case that you use mathematics to help you with applications. It is also the case that applications inspire new mathematics. When you look and you don't have the mathematics that you need to think about an application, well, then if you're like an engineer, you might go and just do a hack, but if you're a mathematician, you kind of step back and back and back and back, and all of a sudden all the people who wanted you to do their application are long gone and have moved on, but you're inspired to do some new mathematics. Okay, so yeah, so we get these graph limits, and they're subtle in many ways. Okay, so processes on networks. So the flow of information is a process on a network. So you have a process, and so you have a network. You want to know how does information flow on this network. So you represent the information itself as a probabilistic process on the network. Is it going to get transmitted to this person or to that person? Spread of epidemics on a network, okay? And we've done a lot of work on this. But basically, you've got a graph again, and the graph could have been formed probabilistically like a preferential attachment graph. But then on top of that, you have a probabilistic process where, you know, if a certain number of your neighbors have a disease, there's a certain probability that you're going to get the disease. So it's a process on top of a graph that has itself been created with a process. And then there are things like viral marketing, which are, now I met an undergraduate woman at lunch who did some kind of propagation. She here? There you are. There you are. So you were doing some kind of propagation, right? You were starting with something and you wanted to know how it propagated, and then you wanted to know what was the seed that you could do that would lead to the greatest propagation. This is that was a deterministic process, but this is a similar kind of process which you can do probabilistically. Okay, so these viral marketing questions are very similar to that. It's what is the seed that I should choose such that if I have this process, so you're really, in order to solve it, you have to do an inverse problem. So you look at algorithms that solve that inverse problem. You know, if I'm going to give out free Windows phones, who do I give them to on this network to get them to spread the most? Okay, and that's very closely related to the propagation that you had worked on. Okay, so algorithms on networks. Now I have my network. I want to do something on this network. So we learned that there can be ranking algorithms for web search. Something else that you can do, since these things are so big, we came up with a sublinear time PageRank algorithm. So it doesn't get PageRank exactly, but it gets PageRank to within a certain probability, and it doesn't even have to read in everything. So there's a whole kind of mathematics, computer science theory area that's forming. Noga Lan, who does graph theory and combinatorics and spends a lot of time here, is working on this. Ronnie Rubenfeld, who's at MIT, is working on this. How do you do these sublinear time algorithms because on certain graphs, because the graphs are so large, okay? And you don't get the answer perfectly, but you get it in a quantifiable way. You get it to within a quantifiable error. Okay, then clustering algorithms for collaborative filtering. So, you know, Amazon says, if you like this book, you'll probably also like that book. Or Netflix says, you've given me these ratings on movies, and now, you know, how much do I think you're going to like some other movie? So what this really is it's kind of like a sparse graph, right? With people on one side and movies on the other side. And a few entries are filled in. How do I fill in the rest of those entries on this sparse graph? Okay, and there is gorgeous mathematics here, which also, in the process, can give you things like improvements of the Netflix algorithm. Okay, so Montanari at Stanford was trying to do the Netflix challenge to win $1 million, which he didn't do, but he did some beautiful work which complements the Candace Tao work on sparse graphs. Okay, so there is really, really nice mathematics, and it's also very related. I mean, you find this. You find that the technological problems of your time actually end up inspiring a lot of the mathematics of your time. And combinatorics and graph theory, being discrete math of networks, is really, I think, a lot of the new mathematics of our time. So it's a great thing for you to be learning about. Okay, algorithms for multicasting and web hosting. So if I want to spread out information on a network, so Tom Layton is an MIT faculty member, a math faculty member, and he just had some papers in a CS conference on, you know, where would I mirror stuff on the web if I wanted people to be able to access it quickly? So I have a graph. Where do I, and if I just have one source of information, it's going to be really hard. You know, everybody wants to see some certain show that's going to be broadcast, and so the website's going to go down. Well, where do I mirror that? What are the points on which I should mirror that in order to have most people able to get things pretty quickly? Okay, that's a beautiful mathematics problem on a graph, and that was the basis of Akamai. Okay, we also did some algorithms for multicasting, which is spreading information out on a network. Then we use the inverse of those for some biology that I may or may not tell you about. Okay, and then fast sublinear algorithms for these viral marketing type questions that are similar to what you worked on. Okay, and finally, algorithms for recommendation systems on online networks. So how do I take something like a Facebook network and use it as a recommendation system? Okay, how would I do that? Okay, so I will talk about that problem a little bit, but let me just go through the fifth of the classes of algorithms. So phylogenetic reconstruction algorithms, which are also used to trace language evolution. Okay, so that I look at the leaves of my tree. How do I try to conclude from that, which is a combinatorial optimization problem? What is most likely to have produced that? There is gene regulatory network reconstruction, which is I look at the proteins that are present in my cell and how do I, in the presence of others, and ask what is the gene regulatory network most likely to have given me that. Or people are also looking at reconstruction of learning processes in a network of nerves, in a network of synapses. So there are these little worms that have about 400 neurons, and so you can actually subject them to all kinds of things and try to back up from there and conclude how they were learning. And we care about things like this because we want to know not only how we learn, but we want to understand things like Alzheimer's. And so ultimately, we have to understand how we learn and then how we no longer function properly. Okay, so if I get time, I will also talk about that. So a couple of specific problems. So recommendation systems on trust networks and reconstruction of gene regulatory networks. Okay, so from a social network, what I might want to do is build a trust network, which could be a directed graph. So let's say I look at my Facebook network and I say, you know, I don't know, you know, most people, I don't know whether I trust their recommendation on music. But here are, you know, 7 people whom I say I trust. So I put a directed link to those people. Okay, and those people say who they trust, whom they trust on music. And for each domain, you would have this. Okay, so you have a graph or a multi-graph. And I assume that each vertex is in one of 3 states. Okay, either the person at that node likes the item. Okay, so they like this piece of music. They don't like this piece of music, or probably most likely they have no opinion on this piece of music. They've never even heard it, okay? And what I would like to do is I would like to propagate the judgments that people have over this network so that I can then get a likely judgment for everyone based on the opinions that I have and the stated trust. And then if you want, I can update it based on feedback later. Okay, so I want to propagate the opinions through the graph, through this directed graph of trust until every vertex has some opinion. Okay? So I could do this in a ton of different ways. Okay? I could do something stupid. I could just take the majority. You might say, oh, it's really stupid. I've got a network. Why would I just take the majority? But I could do that if I wanted. Okay, I could take the maximum. I could take them. I could do a lot, or I could do something much more interesting, like a random walk through it, similar to a PageRank algorithm. Okay, so what we did instead, since there are an infinite number of algorithms that I could come up with, is we said, let's come up with a set of axioms that we believe that the output of the recommendation algorithm should satisfy. Okay? So, how about neutrality? Okay, how about if I flip every like to a dislike, every dislike to a like, the answer flips. I mean, if it doesn't do that, that's really weird. Anonymity. So isomorphic graphs have isomorphic recommendations. It doesn't matter if you're Ann or Sally, you know, if you have an opinion, you have an opinion, okay? If you're sitting in the same node on the network. And some other things. Okay, you know, so positive response. So if I change a 0 to a plus, or a new vertex is added with a plus on it, then everything should get a little more positive. And some other ones. If you've ever heard of Arrow's theorem, this sounds Arrow-esque, okay? So these are all things that, you know, a reasonable person, if you explained it to them, should say, yeah, of course a recommendation, the output of your recommendation algorithm should satisfy this, okay? However, there's an impossibility theorem, okay? So we can prove a theorem, and if you've been thinking about Arrow, you could have seen where I was going, which says that there does not exist a recommendation system which satisfies the previous 6 axioms, okay? It's not as impressive as it sounds because you know, you prove things. You add enough hypotheses to something, you can always get a contradiction, right? I mean, you just keep on going until it's impossible to satisfy, right? Too many axioms. So let me pull out one of these properties that I wanted to satisfy, okay? Well, what we showed is that if we pull out any one of them, we can find an algorithm, we can construct an algorithm which satisfies the other 5. And we can actually tell. One is random walk, it's sort of PageRank-ish. One is an iterated majority, so you do iterated majority out from where you are. And different kinds of things, okay? And it's kind of interesting, you know, we've actually been talking to the ACLU and lawyers and policy people. There are all of these cases that are coming up now where the ACLU is trying to defend people And these big companies keep citing the neutrality of algorithms as if algorithms were all-knowing and could do everything. And so we're actually now working with some lawyers to write a piece for a law journal proving that you can't come up with a search algorithm, which is neutral in particular ways, just to inform the conversation so that, these big companies can't, can't claim that algorithms, that you're not putting something into the algorithm, because of course you are. Okay, but on the other side, we could even be able to use these algorithms to monetize a social network, right? Because how do you monetize Facebook? Well, if you could actually get meaningful recommendations out of it based on stated trust of certain friends in certain domains, that might be useful to you. Okay, so a little while on gene regulatory networks now. So, and this is a huge area. And by the way, even if you have a degree in mathematics, okay, these days it's often hard to get jobs in math departments. Computational biology departments are opening up everywhere, okay? And I know a lot of very good mathematicians who have gotten jobs in computational biology departments at very good universities, okay? So it's something to think about. You should do whatever you're passionate about, but if you happen to be passionate about this, there may be more jobs than something else you might be passionate about. Okay, so standard dogma, DNA is transcribed to RNA is transcribed to proteins. The proteins go and they sit and they inhibit or they enhance the transcription of other parts of the DNA. Okay, so you get this feedback loop, the protein interactome. It's much, there are all kinds of other factors, okay? But I'm going to just treat it like this cartoon for now. Okay, so problems with the gene regulatory network are the source of many diseases. So if we have partial data, how do we infer the network structure? That's a combinatorial optimization problem. Also, can we identify particular nodes on the network which are responsible for dysregulation in certain diseases and certain individuals, okay? What is malfunctioning that is giving rise to this or that cancer, for example? And are one or more of these nodes in combination viable drug targets? Okay, so drug discovery paradigm, there are these things that I was just telling you about. There are lots of other measurements one can take. You feed them all into a computational model. The dirty little secret is they all give you different answers, but if you don't look at that, okay, and so people often don't combine two different things that are supposed to be talking about the same system and are giving you different answers. But anyway, you get points of intervention. Okay, so gene expression data. So let's just look at this. So microarrays tell us which gene is expressed in the presence of which other gene under a certain set of circumstances. So I do some experiment and I see, oh, so I've got this protein with that protein, but wow, that other protein's not there, and so on. Okay? From the different, so there's some background rate that you might normally have of a protein in a gene, but if it's a lot more or a lot less than that background rate, maybe you would think, oh, maybe this certain protein is doing something in this particular pathway, okay? And so I'm going to give it a node weight which tells me if it's differentially expressed or not, okay? So if it's way under or overexpressed, it's going to get a bigger weight. And to get the edge weights between proteins, what I'm going to do is I'm going to take a database on the organism, be it yeast or a human being or a rat or whatever, and I'm going to say, and this is really messy, noisy data, but it says, what are the odds that these two proteins have interacted with each other directly? It's very hard to know if it's direct or not, but assume that we could know in some set of circumstances. Okay. So how do we determine the network most likely to have produced this set of data? Here are 80 experiments, and this is here in the presence of that. What produced this? So now I'm going to go to a mathematics problem. So it's called the Steiner tree problem. So I have a graph, and I have costs on the edges, which I'll call Cij, and I have a subset of the vertices that I tell you absolutely, positively must be in the final set that you choose. So I want you to choose a tree which contains this subset. It can also contain some others and minimizes the cost. So, let's say I have 487 nodes and I tell you these particular 92 of them must be in there, and I want you to get them all in there and have edges such that the costs of all the edges that connect them in a tree is least. I'm almost surely to get them all in there going to have more than those 92, but hopefully not too many more. Okay, and in general, the minimizing tree is going to contain other nodes in addition to the ones I told you must be in there, and those are called Steiner nodes. And we found some very fast algorithms for doing this, which were in fact inspired by phase transitions in physics and lots of other things, okay? So the biological problem is a little more subtle. It's called the prize collecting Steiner tree problem. So here what I'm going to do is, instead of telling you that a set of nodes absolutely positively must be in there, what I'm going to do is I'm going to tell you that if a node corresponds to a protein that's being way underexpressed or way overexpressed, you're going to get a lot for putting it in there, okay? But I'm not going to kill you if you don't put it in there, okay? So I'm not going to kill off the trees that don't have it in there, but you're going to get a lot for putting it in there, okay? And so now I want the tree which minimizes this. Notice, as lambda tends to infinity, I will kill you if you don't put one of the ones with a positive pi in there, okay? I will kill off the tree. But when lambda's not infinity, then, okay, it'd be a good idea to have this big one in there, but if you really have a great solution without it, fine. Okay, so mapping to the biological data. So theCijs are going to correspond to the probability that a connection exists with a minus sign. And so basically what it is that if I think that a connection does exist, if these two proteins are known to interact with each other a lot, I'm going to want to have it in the tree. So it's going to have a very low weight because I'm going to want to minimize Cij, the sum of theCijs. And here, if it's differentially expressed a lot, I'm going to want to have it in the tree. So I want things which are known to connect to each other. That'll give me smallCijs. And I want things which are differentially expressed. Those give me big node weights. Now, in the standard Steiner tree problem, the nodes which are not terminals but which are included in the solution are called Steiner nodes. Prize collecting Steiner tree problem, let's just look at this. Here's the problem. So these are theCijs. The thickness corresponds to the weight. I would really like to include these big fat ones because that helps me with my solution. These big nodes, but I want like thin little edges if I can have them, okay? So I would call this guy a Steiner node because he's pretty small, okay? So I wouldn't normally want to include him, but I include him because he's my connection to those two big fat nodes there. Okay, so it's not, so I call it a Steiner node if it's not very differentially expressed. Okay, in the context of gene regulatory networks, these nodes correspond to proteins which are not very differentially expressed, but which are nevertheless likely to participate. So these seem to be good candidates for proteins that were not known to participate in the pathway. Okay, so the first thing that we looked at was the yeast pheromone response pathway. There are about 4,000 or 5,000 known proteins, about 15,000 known protein-protein interactions. We just went to some known database of 56 different experiments. From those experiments, we said, oh, these are the proteins that are differentially expressed in each of the 56. From each of the 56, we constructed one tree, okay? One bounded diameter prize collecting Steiner tree. We superimposed all of them to get one network, which was therefore not a tree because we have 56 trees. This is how it looked. There were two types of proteins in there. Ones that, oh, they had a lot of weight in them, so we expected them to show up. Ones that didn't have a lot of weight, but really showed up in the minimizing solution. So we said, is this important in the pathway? We actually convinced some biologists to go in and do something which knocked out the corresponding gene. The response pathways failed, so this was experimental proof in a way. Okay? Then we said, okay, well, nobody really cares about yeast, but people care about people. So now we want to do this on human data, which is much more incomplete, huge intergenic regions, so we need fast algorithms. So the data set that we looked at was glioblastoma, which is a horrible, horrible kind of cancer. It's like, the deadliest common cancer, even if you have, surgery and chemo and radiation. Surgery means pulling something out of your brain, so it really does you a lot of harm usually. The mean lifetime is a year, and it's much more common in men than in women, about 4 times as common in men as in women. Okay, so can we find something about the glioblastoma pathway using the prize-collecting Steiner tree? And we used various kinds of data here. How do we choose the route? Well, it's very good sometimes to use a receptor, a protein receptor, because, then things usually attach to that and cascades start from that on a membrane. So we tried EGFR. A variant of this is known to occur in lots of cancers and in many of the glioblastomas. Okay, this was the resulting pathway that we got. If you start to look at the pathway and you know something about biology, which I don't, but my collaborators do, you look at it and there are just tons of places where you say, oh yeah, that makes sense that that's in there. This is like well known to have to do with DNA damage repair, so of course it's going to be in there. In this rendering of it, the colors, so the very red ones are the things that were very differentially expressed or that we expected to appear for some reason. The light ones are things that we didn't expect to appear. And the size of the circle or triangle corresponds to how central something is in the network. So that wasn't put in the data. That, when we're graphing it, we say, wow, this protein seems really central, even though, we didn't put it in, right? But it seems really central. So the top 5 nodes, if I rank them by a kind of centrality, are these. The first one is well known to be active in many types of cancer. Didn't have a super large prize, but it had a relatively large prize. It was differentially expressed. The second one was basically not differentially expressed at all, okay? And not previously identified. What is it? It's the estrogen receptor. So this is the first pathway link between glioblastoma and gender. And just as an experimental test, if you throw in EGFR inhibitor and estrogen, basically estradiol is estrogen together, in culture it does do better in stopping the growth of these things than the EGFR inhibitor by itself. So possible drug therapy, but how do you get estrogen into the brain? God only knows. But anyway, and then we did some multiple signaling pathways with multiple trees, which just gave us pretty pictures of glioblastoma and other things. Okay, so the summary. Everywhere we look, we see large-scale networks. So technological, social, economic, biological. In other words, we see graphs, okay? The modeling and the mathematics on these networks uses, graph theory, combinatorics, probability, game theory, algorithms. The results include new theories, new theorems, so theories like the theory of graph limits, particular theorems, experimental predictions, possibly new business models for something like Facebook, and possibly even new drug therapies. Okay. Well, it models the web like the other one models the internet. But yes, it's on some level a modeling of, and we were actually able to get out some of the exponents that people measured for the web.
Can you say something about the structure, how such a graph such if you take it out?
Okay, it doesn't model everything about the web. For example, in the preferential attachment model, there's nothing that causes significant clustering, whereas the web has significant clustering, meaning if I'm connected to Christian and Christian is connected to Margaret, it's more likely that I'm connected to Margaret. So there are various things. So this only has what we put into it. This is also, by its nature, from the way it's grown, it's a single component. So in some sense, I can get some of the exponents of the web, but I can't get in certain things that I didn't put in to start with. And so people have done a lot of measurements of the web, and it doesn't look like the giant component of the random graph, for example.
Is it like if you take like a few high degree vertices out, then you like disconnect it?
So it definitely has something that you even see in the ordinary preferential attachment graph, which Bolbosch and Reardon proved about the ordinary preferential attachment graph, which is that it has some highly vulnerable sites, okay? So, and people observe this, that, these kinds of networks are much more vulnerable to attack. And so, yes, it certainly has some things like that. And we haven't explicitly proved that in the World Wide Web one, in the directed one, but I'm pretty sure that a similar proof would go through. It's just it's all a lot more complicated in the diagram.
I have a question. Can you tell us a bit about what intern opportunities you have for undergraduate and graduate students?
Okay, so in Microsoft Research, it's almost all graduate student interns. We occasionally have undergraduates, though not that much. So for undergraduates first, our product groups have a lot of undergraduate intern opportunities. And in fact, some of the graduate students we get have been undergraduate interns in product groups when they were undergrads. Okay, so those are more applied things where you'll be told, oh, do this, find this, code this, whatever. In the graduate research opportunities, it's selective, but there are a lot of them. Worldwide, there are about 1,000 graduate internships in Microsoft Research. In the US, it's about 500. They mostly go to CS people, but some go to math people, especially people who do graph theory. And obviously the student has to be good because it's competitive. I think they're really nice experiences. Different advisors, are different from each other, just like in graduate school. Some people, when you come in, your advisor has already thought of a possible problem for you to work on. Others, you'll sit down. With us, since we have so little time, what we end up doing is spending the first 8 weeks of the 12 weeks coming up with a problem, and then working with the student for a year once they go back to their university, having them come and visit us, but that's okay. Usually. So usually papers come out of these things. And I think, for most of the interns I've spoken to, it's been a really nice experience. In our Boston lab, we have about 25 or 30 interns. In the New York lab, about 15 interns, most of them over the summer. And also the theory group in Redmond, which we used to run, which Yuval Perez is in that group, and A.L. Lubetsky, and some other mathematicians you may know. They also have a good number of internships. So in fact, where's Carolla's sister? Okay, her sister met her husband when they were interns in our theory group, and now they're both professors of mathematics at Cornell, right? So there you go.